benchmark, a standard against which other things are measured for quality and value. ADI, the new benchmark material. Prehistoric man first discovers metal from fire. Copper cast in Mesopotamia. Gold cast in Egypt. Bronze casting developed in the Middle East. Flake graphite iron castings first produced in China. Whiteheart malleable iron developed in France. Blackheart malleable iron developed in the U.S. Steel casting process developed in U.S. and Europe. The ancient art of heat treatment is scientifically studied. A novel new heat treatment called Austempering is patented by Grossman and Bain in the U.S. The Austempered microstructure in cast iron is first documented by Flynn and others. Ductile spheroidal graphite iron developed concurrently in the U.S. by Millis and in the U.K. by Moreau. First production ADI component designed and engineered by Tecumseh Products and produced by Wagner Casting Company. General Motors installs ADI rear differential gear sets in passenger cars, realizing a 20% cost savings. Specialized high-volume batch Austempering equipment developed by Applied Process Incorporated and Atmosphere Furnace Company. ASTM specifies 5 standard grades of ADI in both English and metric units. After centuries of metallurgical evolution and decades of equipment technology development, the focused efforts of scientists and engineers have brought these technologies together as ADI, the new benchmark material. Today, there is an increasing demand for these high-performance ADI components, and Applied Process Incorporated and its affiliates are meeting that demand worldwide, with locations in Livonia, Michigan, Oshkosh, Wisconsin, Dandenong, Australia, and Birmingham, UK. The Austempering process is a specialized heat treatment. When applied to ductile iron, it consists of the following: heating the component to a suitable temperature in the range of 825 to 950 degrees centigrade. Holding the component at that temperature for a time sufficient to homogenize the structure. Rapidly cooling the part to the appropriate Austempering temperature in the range of 175 to 400 degrees centigrade. Holding the component at the Austempering temperature for the time necessary to produce the desired Ausferrite matrix and then cooling to room temperature. This can be accomplished in various types of equipment, such as this atmosphere furnace with a specially pressurized integral quench using molten nitrate nitrite salt that is non-toxic and 100% recyclable. The Austempering cycle is affected by the component's configuration and the chemical and microstructural characteristics of the iron. Therefore, the knowledgeable heat treater provides an added benefit for the foundry, the machining source, and the end user at meetings held early in the design cycle. By quantifying, testing, and establishing the correct material process combination for the specific product, the optimum process and property results are achieved. Using specially designed equipment and advanced process control techniques, the heat treater assures lot-to-lot consistency of the product and delivers the desired high-performance properties of the material. Compared with conventional grades of ductile iron, ADI has over twice the strength for a given level of ductility. ADI has remarkable wear resistance for a given hardness level when compared with other materials. The ductile iron casting process uses recycled ferrous materials. Ductile iron can be easily cast into complex shapes. Therefore, ductile iron is a near net shape technology. In turn, the Austempering process produces highly repeatable dimensional response, thus giving the manufacturer significant flexibility in manufacturing. ADI has excellent dynamic properties, which can be greatly enhanced by fillet rolling, shot peening, and grinding. Its gear properties make it competitive with carburized steel. ADI's noise damping capabilities provide quieter running components that are superior to both steel and aluminum. ADI is 10% less dense than steel. Thus, even for a given shape, an ADI component will be 10% lighter. Because of its excellent castability, ductile iron can be cast to a nearer net shape than either a steel casting or a forging. Therefore, not only will you buy less material, you will machine away less, and the resultant part will be lighter in weight. An ADI component uses 50% less energy per unit of weight to produce than a steel casting, and 80% less energy than a steel forging. And ADI is stronger than microalloyed forged steel with comparable fracture toughness. Because of ADI's unique osferite matrix, for a given level of hardness, it will exhibit significantly better wear resistance than conventionally hardened steel. ADI has successfully replaced manganese steel and carburized steel in many wear applications. Ferritic ductile iron has better machinability than even free machining steel, creating significant savings in the machining process. By machining components in the ferritic condition and Austempering after machining, machine feeds and speeds are increased and tool lives are greatly extended. In addition, machining of ductile iron produces a small discontinuous chip that can be easily stored and recycled. While prices vary worldwide, on average, ductile iron castings cost significantly less than steel castings or forgings. In North America, when the cost of Austempering and transportation is added, the price of an ADI component is typically 20% less than a comparable steel forging or casting. Additional savings are realized by machining in a soft, as-cast condition. Today, when one thinks of lightweight materials, aluminum comes readily to mind. But low density alone does not necessarily make the lightest component. ADI is typically more than 3 times as strong as the best aluminum castings and forgings, and ADI weighs only 2.5 times as much. Additionally, ADI has over twice the stiffness of aluminum. That means that a properly designed ADI part can replace an aluminum part as a weight savings. Given that aluminum can cost up to 10 times as much per unit weight, the cost benefits of ADI become apparent. ADI is now being applied in virtually all markets. The heavy truck industry utilizes ADI components in suspensions, engines, transmissions, wheel hubs, and bracketry. The light car and truck industry utilizes ADI for camshafts, crankshafts, timing gears, suspension components, constant velocity joints, differential cases, differential gear sets, and transmission components. The construction and mining industries employ ADI components for bucket teeth, chain sprockets, ore crushers, jackhammers, bridge and highway parts, ground engaging and structural components, and a wide array of hardware. The industrial and material handling industries utilize ADI for conveyor components, pump components, structural components, wear plates, trolleys, gears, and other hardware. The railroad industry uses ADI for suspension components, car wheels, maintenance vehicle components, and truck and car hardware. The agricultural industry uses ADI for plow points, till points, fertilizer knives, PTO components, grain transport and grinding, and tractor and implement components. The defense industry is utilizing ADI for medium-duty track and suspension components and various armor and ordnance applications. By varying the OSTempering process, a wide range of properties can be delivered. From tough dynamic structural components to hard wear-resistant parts for high wear applications, Applied Process and its affiliates can make ADI work for you. When compared to other metals for strength to weight ratio, ADI is the new benchmark material. When compared to other metals for manufacturing flexibility and wear resistance, ADI is the new benchmark material. When compared to other metals for low energy consumption and recyclability, ADI is the new benchmark material. When compared to other metals for low manufacturing cost, ADI is the new benchmark material. When considering a high-tech material for your high-performance components, choose ADI, the new benchmark material.